All right, folks. What I'm going to do in this video is discuss the section 2.4 from the textbook. All right. Section 2.4, the name of it is the precise definition of a limit. Okay. So I wrote it all up there. It's kind of wordy, so don't worry about it right now. But the way that we've been sort of discussing limits so far has been kind of loose, right? Kind of intuitive, but a little bit loose, not super precise, right? So we want to have a way, at least, of describing it with a little bit more precision. Let's look down at this statement, because this is all about how we're justified in claiming that a limit exists. In other words, if I want to claim that this statement that I just boxed in there, remember, we read this as the limit of the function f as x approaches a is L, right? Or we can read it as the limit as x approaches a of our function is L. Or simply kind of just say the limit as x approaches a is L, right? If we know what function we're talking about. And what that means is for this function f is if x is getting close to some particular a value, as x gets close to some particular input, then the corresponding function values or corresponding y values are approaching some value, some number L, or maybe some infinity, right? So that's the concept. And the way that we've kind of been describing that is we say, well, as x gets close to a, the function values get close to L. That's what we've been saying. And that whole phrase gets close to, or that concept, that's what needs a little bit more precision, right? That's not very precise. How close? How close do we need to get our inputs if you want to get your outputs within some specific range? That's really the heart of what this is, okay? So I can leave that boxed. You'll notice on the homework on WebAssign that there's a pre-lecture for 2.4. I'm not going to do anything else with 2.4. In other words, there's no real homework assignment for it. I won't ask you any paper assignments. It won't be on the final. So this whole concept, I want you to just appreciate it, see that it's out there, see that it's possible to narrow down these limits in real precise terms, and I guess be able to. More so, I just want you in the future to be able to claim that you've seen this before. So if you do see it in a Calc 2 class, you might see it. If you ever take Math 130 for any math majors or math minors, and I encourage you, if you like this stuff, if you really like calculus, like these ideas, consider taking some upper division math. So if you're a physics major or an engineering major, things like that, it doesn't hurt to have a background in math as well. I'm sorry, a minor in math looks good. Computer science, same thing. So anyway, in those classes, in that class, this upper division calculus, you'll do this a lot. So let's just set the stage. So first, I'm just going to read this through. It's kind of really wordy, so I'm just going to read it, and then I'll try to break it down and explain the different parts, okay? And then on the pre-lecture, you're doing a few exercises, some of the examples from the text where you kind of just follow what they're telling you to do, and hopefully the concept makes sense with some real numbers involved. First of all, this opening part, let f be, so let some function f be defined on some open interval containing the point A, okay? As far as we're concerned right there, don't worry too much about the open interval part. But what that means is you've just got a function f, and it's defined on some kind of interval. Maybe it's defined elsewhere too, but at least on some interval surrounding some particular point that we're calling a, we're just assuming that the function exists, okay? A is just some particular x value. So we need to, if we're going to talk about what's the limit as x approaches a for some function, then the function should exist around a, right? So that's what we're saying. Okay, so suppose we've got that scenario. We've got a function. I'll draw a picture to get it, but we've got that. Then, if we want to make this claim, if we want to write that the limit as x approaches a of our function is some number L, right? Then what do we need to do that? How do we need to show precision for that? So if we've got this scenario, then we're allowed to write this notation. We're allowed to say that the limit exists if this whole part of the piece is satisfied. That whole conclusion, which is some more if-then statements, and so forth. All right, and bear with me because this is complicated. We're using Greek letter. This is an epsilon. Looks like a letter E, kind of rounded little E. This is a delta, a lowercase delta. If you kind of angle your head, it looks like a little lowercase d, sort of. That somebody. They're actually fun to draw if you can get the hang of it. But yeah, so we've got this epsilon, delta, and what we're claiming here is that epsilon is positive. Then delta positive. What that means is positive numbers, and we're gonna sort of interpret though epsilon's like a small positive number. Because since we are trying to capture the idea of a limit, getting close to a value, this is going to sort of be some kind of little region around the function value that we want to get. Okay, so remember, the A is going to be a particular x value, and then L is going to be a particular sort of output, sort of function value in a way. Okay, so what we're saying is the limit exists if for every epsilon, for any small positive number you can think of, for every epsilon, then there exists some other small positive number, some delta. So in other words, if you tell me the epsilon, you tell me this epsilon, I can then choose some delta that's going to work for this. That's the idea. So for every epsilon, there exists some delta such that, and then we've got these inequalities here. So I'll read the inequalities out, but then I'll try to sort of paraphrase what it's saying. It says such that if 0 is less than in absolute value x minus a is less than delta, then in absolute value, the function value is f of x minus L, which is going to be our limit, is less than that small number epsilon that we chose. Okay, so what does that mean, right? That is a little bit kind of probably weird to interpret. So what this says, again, for every epsilon, so you guys tell me a small number, then I can find some kind of small number, some small little range of x values, essentially, such that what this inequality means is this thing, the absolute value of x minus a, that means sort of the distance between x, any kind of x value that I can think of, and the target x value a. I'll draw that in a minute. But in other words, what we're going to do is sort of create a little window, a little window around the x value a. And sort of the radius or the length of the width of that window is going to be bounded by our delta. All right? And what we're saying is then if the limit as x gets close to a, if the function values are supposed to get close to L, then what we're saying is, okay, if I can bound this distance, I'm just going to consider x values whose distance from a is less than this particular small number, then what that guarantees is this absolute value, what that guarantees, if those inputs are satisfied, then the function values, the distance between the function values I'm getting as I got close and the actual limit is less than kind of the small requirement that you gave me to begin with. Okay. If you sat through all that, you may still be thinking, what the heck is he talking about, right? Still a little bit kind of weird. Let me draw a picture, and I think a picture is really going to help. So, I'm going to get rid of this definition. If you didn't copy that down, pause it, rewind it, copy that down. It's in the book. It's on page 106. It's in a big box labeled number 2. What's number 1? Anyway, curious. Okay, so let me draw a picture of that. Okay, so I got x-axis, y-axis, and got some function. Just call that function f. Let me make it a little bit more curvy. Okay, got some kind of function f. That looks like a nice, maybe a smooth polynomial. And remember, we wanted the function f to be defined for some value a, and then, or at least around the value a. So let's say something like that, okay? So I'm just putting a right here. These open brackets kind of mean there I've got an open interval on my x-axis containing this particular x value, which I'm calling a, okay? The only reason, don't concern yourself too much with this, but the only reason why we say an open interval is we don't want a to be an endpoint of the interval. We want it to be what's called an interior point, which means it's sort of inside, has space on other sides. And so that's why we use open intervals. Technically, an open interval doesn't really have a endpoint in the sense that I can mark what number that is, but there's no largest number in this set, right? However close I get to those parentheses, see I'm in the reflection of the light right there. So anyway, so I got some open interval, and a is somewhere kind of tucked in the middle of that, right? This is a nice smooth continuous function. So the function value of a is just up here, and that since I have a continuous function, then based on our sort of layman's definition of continuous, I can pretty much conclude that that the limit is going to be that same point. Kind of slowly talk right there. Let me trace up from here, right? So I'm going to come over here then, trace that way, and it's true that this height right here is f of a, because this function is nice and continuous, right? So that point exists. But it's also true that that's L. In other words, I'm going to write that the limit as x approaches a is whatever that height is. I'm going to call it L, because this is a nice continuous function. So as I approach from the left, I'm coming down to that height, approach from the right, right? So we can say this is L. And remember what our claim is this, that the limit as x approaches a, for this, I'll label the function f, for this function f is this value L. All right. So I've had my my value a. I just came up and then I just went over, found the limit. Now, so again, this is imprecise at this point. I'm saying as we get close to a, the function values are getting close to L. Well, how close do I need? So let's say you tell me a small epsilon. All right. So you're going to give me an epsilon. So you tell me, you give, let me write it sort of as a process. You give epsilon, a small little epsilon greater than 0. And our ultimate sort of requirement, the thing that we need is we need this, f of x minus L in absolute value bars to be less than epsilon. All right. What this means is that the distance between f of x and L is less than epsilon. And the absolute value bars are just because for a distance we want a positive number. If I break those absolute value bars, what you get out of it is this. That means the difference between f of x and L must be sandwiched between a positive and a negative epsilon. All right, that's how that works. So in other words, if this quantity is sandwiched between the positive and the negative version of our number, that's why we require that epsilon be positive, then these mean the same thing. All right, and so then what we get is if we add, how do we want to do this? If we add L to both sides, or all three sides, all right, then what do we have? What we're looking for is this. We want the f of x to be sandwiched in between L plus this epsilon, and sandwiched between over here L minus that epsilon. All right, and if I'm losing you, hang with me. Okay, so this is what's required by that big statement that I had earlier that I erased. The very bottom statement said that we needed this to be true, ultimately be true. And that means this. What that means is that we need to bound our function values, these f of x values. So for different x values, we need to bound the function values between L plus epsilon, so plus a little bit, and L minus a little bit, right? So here's L, right? That's my limit. Let me draw this little, let me make it a little bit smaller. Bear with me, guys. Put a little round bracket like that, and a little round bracket like that. Okay, so what I've done is sort of create this little stripe around that limit. All right, and if you see what I did there, I kind of traced over from that little upper bound and this little lower bound and see where I intersected the function right there around that point. Okay, so remember, epsilon's a small little number. So L plus epsilon, if this red dot is L, then up a little above it is L plus that little amount, right? So in other words, that little distance right there between the red and that little purple cap up there, that little distance is epsilon, right? So that little top of that line, this dotted line, has that height of L plus epsilon. And this one is L minus a little bit. So L minus epsilon, okay? So that's the idea. You gave me an epsilon. You said if I'm telling you guys that the limit as x gets close to this a is this height L, then you come back at me and say, well, wait a minute. If it's really getting that close, then how about you guys give me this little window, kind of like a little tolerance. You guys are saying, fine, if it gets close, then make it that close. Show me prove to me that there are x values that we can plug in that will be within this little stripe or this little window around our limit. That's what's happening. Okay. If I seem sort of enthusiastic right now, it's because I think this is kind of cool, this concept right here. All right. So remember, you give me some kind of epsilon, then, as we wrote up top, then there exists some delta, some small positive number. So I'm kind of making it a back and forth between you guys and me. So you give me the epsilon, then I give some kind of delta. Right, so I'm going to come up with some little number, delta, some other positive number, which is going to be a distance on our x-axis. And how do we want that delta to work? Well, ultimately, what I want to be true is this, that x minus a, I want that distance to be greater than 0, so a positive distance again, and less than delta. All right. So what I'm looking for, if you rearrange that thing a little bit, I want to choose x values that are this. They're either between a plus a little bit, plus whatever delta I'm going to require, or a minus delta. Okay, so you can play some rules with some inequality, absolute value rules, and rearrange this. But this is what kind of restriction I need to look at. So again, for what x values is it going to be true that the f of x values are within epsilon from our limit, right? That's our goal, is to get that true. We want function values. So for what x values is that going to be true? For these x values that satisfy this. Okay, so how do we decide what delta is? Or how do I decide? You guys picked epsilon, now it's on me to decide what delta is. Let's do this, all right? So remember we had the L up a little bit, L down a little bit, right? That little stripe. And we traced over, and I found that point intersected the graph right there, or hit the graph, and then the other point hit the graph right there. Okay, let's just drop down vertically and see where we're landing on the x-axis. Okay, so drop down vertically, and I hit the x-axis right there. All right, so maybe about, I don't know, you can judge that distance, right? So you can judge that. This green dot, if I drop down, and I'm freehanding this, but it looks like it lives a little bit closer to our x value of a, right? Oops, I should draw a little bar there, but that's fine. Okay, so I came to that spot and I dropped down. I came to this spot and I dropped down. All right, so what am I going to choose as delta, right? Remember, it's my responsibility to choose delta. What I'm going to do here, and again, this is real loose. There's no actual like figures or numbers to reason out. But what I'm going to do is I want to pick the smaller distance and claim that distance is delta. All right, so I want to choose that little window right there. And all of these inequalities have strict inequalities, no equal bar. That's why I'm using these round brackets up here. So I'm going to use a round bracket right there, right? So I want to choose that little, draw that little horizontal line. That little gap right there, that's going to be my delta. And that means on this side, I'm only going to extend that way. All right. And there we go. I've done it. So in the picture now, I've done it. Because what I've done is I'm claiming now, you told me how close. So I'm claiming, at first, let's back this up. Take a deep breath. At first, we're claiming that the limit as x approaches a of f is L, right? That's what we were claiming last week when we first introduced this stuff. What we're saying now is that if I'm telling you that the function values are getting real close to this value, L, then you're saying, well, how close? And you're telling me how close you want it. So you chose epsilon, and you said, I want it this close, right? Centered at that little thing, but I'll give you a little bit of tolerance. You give me a little bit higher, that's okay, because that's pretty close. And you can be a little bit lower, but not too far. I want you within that distance of epsilon. And so I said, okay, I can do that. I can guarantee that. Let me trace over here, drop down, and then I'm going to choose that small distance right there, the smaller one, and let that be my delta. And now what the conclusion, if we read through the theorem, again, or the statement of the whole process, for every epsilon means that you can choose any one you want. So that's why I was saying you guys can choose that. So for every epsilon, or for all epsilon, then there exists some delta. So in other words, this delta might not work. If you shrank your epsilon, I might have to get closer to A, right? But for this particular epsilon, there exists some small interval, some small value delta, such that essentially that if x is within that little, from A, if x is within that little distance from A, either A plus delta or A minus delta, then the function values are within our tolerance where we need. And that's really the way it goes. All right. Why did we have to choose the smaller distance right there? Right? What if we chose the larger distance? Well, if I said let delta be this value right there, that distance, then what I'm saying is from here, right? But the whole thing is we're going to get sort of that symmetric interval. So then I'd have to extend, if delta is that big, then over here, then this purple is A plus delta and A minus delta. These points are maybe too far away, right? If I trace up from some of those x values, I'm hitting the function up there, right? And maybe that's outside of the stripe. That's outside my tolerance. So you kind of want to be more restrictive, right? The one that's closer, it's even though these function values might work too, but it's okay to be more restrictive. And what we're doing is guaranteeing that if you're in that blue interval for your inputs, then your outputs are within this purple interval. And if you can do that for any number, if you shrank your number, your epsilon, I would just shrink my delta and get a little bit tighter, right? There we go. So that's your precise definition of that limit. just around hitting 20 minutes, so good place to stop. There we go. Again, don't stress too much about this. I'm happy to talk more about it if you want to send me any questions from the Ask Your Teacher messages from this section, or during office hours, or just through email. It's a cool section. If it makes sense and you want to play around with some calculations, maybe look at the ebook, or ask me for some suggested problems. And again, if you feel like math, either major or minor, is in your future, then at some point you might want to tackle that. All right, there we go.